come to the last presentation before lunch. Later on, we will have pizza here. Now I'm welcome Axel and Edras from Microchip. They talk about how we can use the open source with the chips.
Okay, hello everyone. First of all, thanks a lot for having us here. We are Edras and Axel. We share an office at Microchip in Heilbronn, Germany, which is one of our many locations we have in Germany and all over Europe. Today we'd like to share with you our approach of using open source software in industrial IoT applications. Edras.
Yes, you should be thinking what Microchip. We are a hardware vendor. We sell chips like PIC and AVR, and what we have to offer for open source, or what we are handling with open source in our chips. So just a brief overview about Microchip. We are not selling any chip today here. So any one of you have already programmed a PIC or an AVR? Yes, 1, 2, 3, 4, 5, nice. Or an Arduino? More hands. Arduino is also Microchip, so so this is nice. But Microchip, we have not only microcontrollers or microprocessors or FPGA. We have a bunch of other microcontrollers or small microcontrollers for AD, filters, amplifiers, encryption and security. If you have a hardware that you need encryption, we have right solution just to glue, just glue over the bus, and then your circuit, the communication is secure and encrypted. We have LED drivers, digital to analog converters, power drivers, motor drivers. My main area inside Microchip is motor control and predictive maintenance with AI ML, so running models on the controller to do predictive maintenance. And optical networking, USB, wireless, so on. So if you need anything in a new project, you have a new idea, a new concept, please give a try to Microchip, and then we are glad to help. Okay, the next point. This is the last slide from products from Microchip. Here we have a restructuring inside Microchip, and then we have a new division for entry level where we have our PICs and AVRs, 8-bit. Here we have the DSPIC, where we have a DSP coprocessor. It's a 16-bit device. And for the 32, we've had PIC MCUs and SEM MPUs. We have single core, dual core, and we have our latest device, the PIC64. It's a RISC-V platform, where we also have a partnership with Ubuntu Canonical, and it's running here on this device. So if you want to give a try with our Linux device on PIC64, but we have also portability for Buildroot and Yocto. This is all about chips. So, talking about smart things. Nowadays, we talk about smart buildings, smart cities, smart manufacturing, industrial 4.0, and so on. I think it's higher now. How we can connect all these devices in an industrial environment. We have protocols, we have interfaces, and for all of this, normally, if you are talking to embedded engineers, they think about bits and bytes and registers. But then this is not scalable. How can we connect our low-end devices, our 8-bit microcontrollers, with this high stuff, with these cloud services, with these protocols? And from the sessions that we got yesterday and today, I think it's very inspiring to hear about rewriting this concept and Zephyr, and so these aspects, because everything is connected. So here we have a bunch of nice and buzzwords of like TSN, EtherCAT, 10-base T1S, and lots of a mixture or a salad of letters. But then how we put this all together in a smart manufacturing. This is the aim of what we are talking today. And if we go one step higher, then we need to connect our devices also in smart building, because then, or in our homes with Gardena. So how to connect our lawn mower to our system or with our smart home devices and so on. Because here we have smart meters, power management, we have solar panels, and everything is connected. And how to handle this? And going one step above, we are talking about smart cities. We have street lights, we have traffic control, and at the very end, at the edge, we have these small controllers with an 8-bit device, 16, 32-bit, or 64, and we need to connect all this, and they need to talk to each other. And nowadays, previously, it was enough. We made a program, we flashed the device, it's on production, it's done. But now, if we have a new model, we quantize a new model and we reduce, and now it fits into 3 kilobyte flash, our model. It's not like 48 gigs or how they talked yesterday, a model that was huge. But then we need to fit this model inside some K bytes in a microcontroller. It's feasible, it works. But then how we connect this and make it connected and useful. And this is the aim of today, because I got a challenge. When I joined Microchip 3 years ago, and inside Microchip, we have lots of hardware engineers, and they think, okay, we have a new product. This one, Micro E T1S module. It's a T1S network controller, and I need to make a platform. We have like this Arduino-based, or looks like an Arduino-based. We have some shields that we can attach several sensors. And our controllers. It could be a Cortex device like a SAMD, SAME, or a DS-PIC, or a PIC, or the new PIC32CK. And the manager said, okay, we need a demonstrator, and please glue this all together and let's make a demo for our customers that is smart, make stupid things smart. So, okay, challenge accepted. But first of all, what is T1S?
Yeah. So you might have wondered what T1S is, so maybe a question to you. How many of you have heard about single pair Ethernet? Oh, quite a lot, yeah. And what about 10-base T1S? There's only 2, so yeah. So 10-base T1S actually is a standard of Ethernet standard. And we are seeing a bright request for interfaces like this. So in comparison to traditional Ethernet connections, the single pair Ethernet, instead of having 4 or even 8 wires with the Ethernet, we now have only 2 wired, the so-called twisted pair wire. For the German language people, you can say it's called Klingeldraht. Yeah. So actually, what the T1S tries to do, so first of all, the 10 of the 10-base T1S name stands for 10 megabits per second, and the T1 is the one twisted pair, and the S is for short distance. The special thing about T1S, it's that it's a multi-drop solution, so it's not like the traditional Ethernet connection, which is a point-to-point connection. So with 10-base T1S, you can have up to 8 members in the network, and this up to 25 meters. Yeah, with the multi-drop solution, there comes a problem of collisions in the bus. So that's why we're having in the physical layer we're having the collision avoidance implemented. Yeah. So let's talk about the big advantage of single pair Ethernet protocols and connections. So as you can see on top, in traditional applications, we have several software stacks using different interfaces. And with the single pair Ethernet connections, you have only one protocol through or you can use only one protocol through all the physical layers. And this makes it way more easy to for example, encrypt your communication, and with this be prepared for challenges like cyber resilience act. Yeah, back to Edras.
Okay, going back to our challenge, Microchip offer a dev tool called Melody or Harmony, depending on the bit width of the controller that you are using. And if you start with a new project with a controller, first you download the datasheet, and then you read 1,000 pages to understand how the ADC works, or how the SPI or I2C work, and have fun. This is not so fun, but then we do provide with our dev tool, you select a controller, you take Harmony, and then you select like a sensor with this weather click where you have air pressure, temperature, moisture, and so on. And then you do produce a software, and it runs quick and dirty. And so you have the software running. And most of the engineers that are just testing, making this project, I need that the project runs, they are happy with this. And many of them are not even using a high-level C language, they are using assembler. So they get access right to the register, and they are happy with this. The problem, it's not scalable. If you have any change on the hardware or on the definition or on the platform that you want, or a new requirement that a marketeer just wonder, okay, we have a new buzzwords, we need to implement this. It's impossible to do this in assembler or even on C. And then doing best practices, and this was the first barrier that I found at Microchip, was to convince the guys, hey, we need to do best practices here to sell our parts, because the customer, they don't want to be relied on a tool that we connect the hardware tightly to the software. So we define an interface here, and then we have a software with a contract, and then we can communicate with our hardware through this interface. This is for open source, this is normal. But for hardware engineers, embedded software engineers, it was not that easy to understand what are the benefits of an interface. Just splitting the hardware stuff from the software stuff. Now, okay, we have an interface, next step. We have a problem, because now we have an interface, and we have different softwares for different processors, because our module has an interface, we can communicate over it, but then on that interface, we still have differences on processors or bit-wide, like a PIC18F, 8 bits, 16 or 32-bit. We have different patterns on how we can communicate. It costs time, effort, keep different software versions, and so on. Hardware changes demand deep software changes. And for open source, is already know that. But the solution is to prepare a whole interface. So we suggested for this new Blue Wedge reference design, and this is the project, this is the name of this project, this is Blue Wedge AIoT. AIoT, A is not for artificial intelligence, it's for adaptable, so easy to use and scale. And we defined a whole layer where we have definitions for different boards, where we did the connection from our dev tool to the main application. And for different sensors, we have also the whole layer, hardware abstraction layer, to communicate with different sensors. And we have contracts between applications and sensors. And these contracts, they are well defined. And now, with this approach, and it was really new for even people inside Microchip. Okay, now we have a portable solution that we can just exchange the controller or exchange our hardware. And this goes against a hardware vendor because they want to, okay, you need to use our parts. But then, if we do not allow our customers to be free to have this choice of exchangeable, they were not even going to select us. So this was a mind-breaking thought, and we are spreading this, and then we are, with this board, now we are leveraging this solution in America, in Europe, in Asia, and I think it's a big answer for that. Okay, Microchip is not already a closed software solution. We are open now, and this project is already on GitHub. It's not yet public, but we are just handling the last parts, and we invite customers to join this project to have a look. And on what I presented, the customers, when one of them said, okay, we are looking for this now. And we have this sales demonstration where we have our boards running, Raspberry. Raspberry is not from Microchip. And T1S, it's a small short track here, a router. And we are running Node.js, Node-RED with MQTT. And the next one is the lightweight IP. This was also a breakthrough. Microchip support is also part of the Open Alliance. It's a connector from the lightweight IP implementation, and we are not using our own development. This is an open source project that Microchip is part of. And we do support this library to make it possible for this very low-end device to send packages with Telnet, MQTT, or TCP stack without using Microchip parts, and just downloading, making a Git clone of the project and compiling it. So it's a very simple example. So where we have the Curiosity board. So this is the name of this board, Curiosity. And we connect over TN-based T1S to a Mosquito broker and Node-RED. On our new device, we have also the hardware secure machine. And then we can generate the certificates and keys and handle this exchange and then make the communication secure. This was our prototype first, our proof of concept. And then after that, I got a meeting with a customer who was curious about it. And they do produce gas sensors, because for heat pumps, they are mixing hydrogen to natural gas. So we have a different mixture of gases, and then we need to handle the perfect time or the perfect concentration to burn and have the lesser emission of CO2. And then in this case, they got a sensor, they hired a student, a master student, to make this project work, and then the master student was struggling already 3 months long. Okay, we need a demo, okay. And then they called me. I present that because you don't need to use this. We can use our open source stuff. And really sad, from the concept, we got on a couple of 180 minutes, we get the prototype up and running. This was different at Microchip because normally, okay, you go there, here's our sensor controller, and then here's the software, have fun. But we are FAEs, field application engineers. We are glad to help this and bring this new kind of embedded mindset to the market. And then the project evolved, and we have this new Blue Edge AIoT, where we have several parts. Here, we have 3 Curiosity boards. Here we have Cortex MPU running Mosquito broker there, and we have an unsecure network Here we have sensors for air quality, pressure, moisture, volatile organic VOC, I don't remember what is the C, and it's connected over T1S. And here we have another network, and this network is running at 8 megabits per second. So if you have a project that if you want to replace Modbus or UART or so on, this is a nice approach. So you are connected right on the way with Ethernet. And this network is a TSN, a time-sensitive network. So we can send packets with exactly the time that we want to have and go to this other part that we have, we escalate from 10 megabits to 2.5 gigabits on this switch. Here is also running a Mosquito broker. And in that case, we do service orchestration on this right part here above. This is also Raspberry, but here on a fair or trade shows, normally we don't have access to internet. On this demo board, we are emulating here a service orchestration where all the intelligence is distributed. What I mean with this? The final boards here, it's running a single piece of software. It's the same software, and it recognizes which model is connected to the board. And connected to the board, it detects, okay, it's a weather sensor, it's a pressure sensor, it's a distance sensor. I do produce a topic, and then I send, okay, for this topic on MQTT, I collect the data and send it to the cloud. And the only responsibility of this board is just to collect data and send to the topic. And on the cloud, it detects, okay, we have an increase in temperature, we have an increase in moisture, so we need to take an action. So send this message to this topic, and the orchestration, the connection between the system, the message arrives at this guy here. This is the Smart IO. And then, okay, now I got a message from our broker that we need to turn on the fan or blink the lamp here for warning. So without changing or without flashing the device again, we can change, and we are able to change the behavior of the system. And this is smart because now we can demonstrate with many different parts and using open source and using best practice with modularity, don't repeat yourself, and whole abstraction layers. We can showcase that, yes, we are able to deploy modern applications and be dynamic enough to adapt ourselves to what the market needs. So we ensure compatibility across platforms, and we do support IoT and edge computing. So with a small smart controller like this one, we are connected from 10 megabits up to 2.5 gigabits. So we are communicating.
So these news are not, to be honest, not that recent anymore. We kept the slide because we really like the cat, but we recently became a member of the Zephyr project. So yeah, thanks a lot. So yeah. Yesterday we heard that bigger organizations like Siemens are sometimes having a hard time sharing their IPs with open source project, and yeah, kind of the same happens for Microchip, but yeah, now a slight transition happens, and getting a member and contributing to the project is one of the first steps Microchip is doing in this way. Microchip is focusing strongly right now on providing device trees for all of our devices. There are lots of devices already available in the mainline code, but way more device trees are coming soon. Okay. Oops. So this morning, Mark and Reto already shared all the nice features of Zephyr, but maybe go again for example, for the hardware abstraction layer. Edras mentioned it. It's a really important thing for our IoT applications, and Zephyr is using the principle of device trees, which you might use from embedded Linux. On top of the hardware abstraction layer, we have the kernel and OS services. Here, the Zephyr is nothing different than other RTOSes. It's just the services we know. For example, creating tasks, handling the tasks, creating semaphores, mutexes. What really differs Zephyr from other RTOSes is the middleware, which comes with the Zephyr RTOS. For example, the stacks and all the driver supports. And on top of this, we have the third-party libraries. Mark mentioned them earlier this morning. For example, the MCU boot, Wolf SSL, and the lightweight IP stack Edras mentioned is available as well. Another really important thing about Zephyr is the safety and the security topic, which has Zephyr already in mind, which again prepares us for the topic Cyber Resilience Act and similar things that might come in the US and other countries. Okay. Talking about benefits of Zephyr Zephyr comes with a huge amount of board support. To have numbers, it's more than 750 boards. And some of them are microchip boards, and of course we wanted to use them for our project. In addition to the board support, we also have sensor and driver support. For example, the T1S5 we mentioned earlier is one of these drivers. It's available in the Zephyr mainline as well, and of course we use this for the project as well. Other than the T1S5, we of course have drivers for the I2C, SPI, and all the other interfaces as set. Okay, so having all the tools with Zephyr available, we of course wanted to use them in our project, and as you can see, the structure Edras showed earlier slightly changed. So now we have, for all the hardware abstraction layers, we have the Zephyr device trees, and for the driver level, we have the T1S5 and all the sensor drivers replaced by Zephyr and now we have a really open source project now, which we are really happy about.
We made a rewrite.
Yes. So we heard about the rewriting code again yesterday, and that's what I did with Edras's code. So I replaced all the bare metal code by Zephyr functionalities.
And it was good to mention here because we established well-defined contracts and interface, so it was easy just to port the bare metal implementation made by Melody and Harmony, these microchip tools, for Zephyr. So it was good. So take the time to do the homework and do the interface and so on when you are doing embedded software, because it is worth it.
So this brings us already to the conclusion. Edras, do you want to conclude?
Yes, here about Zephyr, before concluding here, as Microchip joined Zephyr as a member, because since now we see on the community this porting for the board for the SAM-E54 was made by the community, and Microchip was only receiving this from the community and not taking advantage of being open source. And now, as a member, we have some definitions. We have a port we are working on a port for the DSPIC, also Zephyr for motor control. So we have real-time on 20 kilohertz PWM and get interrupts, so we can do motor control using Zephyr. This will be released probably end of this year. We have portings for Zephyr for multiple boards that we are working on right now, and also for our, I think, even for the PIC64.
Yes. This is already available in mainline, so for our multi-core RISC-V controller, there is full Zephyr support already available.
Yes, and this is great news because it means, like as Zephyr said, it's a wind of change. And we have this internal concentrated software development inside Microchip, and now we are opening ourselves to be open source in this new path. So regarding this demo, now here we have also Zephyr, and we have our complete ecosystem integration from the low level up to the cloud services. Here we use the only well-defined open standard protocols. We are not closed anymore. And we are enabling high speeds where it was not even thought about. Because when you are talking with small controllers communicating between each other, we need to think about, okay, I need to transmit, I need to send data from A to B. How to be flexible enough that I can enhance future technologies to be inserted right here. So Zephyr is one answer for it. T1S, Ethernet and Ethernet protocols are belongs to this answer. And I think having an open mind and be open for what is new there, it's a very good way to behave. So I think this is all we have. These are our emails, and thank you very much.
Okay, thank you very much for the great talk here, and also congratulations to the right decision to provide drivers for Zephyr. So definitely the best choice you could do here for the company, and also what we expected here at Siemens as a customer. Easy onboarding, easy to use, and also then easy to maintain. My question is, I'm missing here a little bit the part of the Linux drivers, right? So do you have, or one question specific, do you have the T1S driver or the SPI driver also available for Linux?
Yes. Yes. Even on the Raspberry Pi, if you get the default installation, it's already included there.
Okay. Yeah, but is it really available on mainline and not in user space?
Good question.
It's a good question.
Have you checked it, or?
I think so. It's missing, right? So that's
okay.
I can check it because the main developer of this driver, it's Thorsten Kummermeer. It's located in Karlsruhe in Germany, and he's taking care about it. So I can ping him, and then I will get this information.
Yeah, thank you. To follow up on that question, in general, what is your mainlining strategy, both for Zephyr and for the Linux part? So are you going upstream first with your enablements? I mean, obviously you have maybe a backlog right now that you can have to catch up first, but is this a part of the strategy? If I come to you as a customer, do I get a board support package from you still, or can I also pick my enablement from the mainline components? When can I go for Zephyr and have everything enabled there? I looked if your PIC65 chip is in mainline. It's not mainline Linux. Is there a plan for that, or what is the strategy in general for these kind of things?
So unfortunately, I don't have the slide with me, but what we are doing is we have a fork of the Zephyr RTOS project, and we are developing with this and then pushing back to the mainline code. So yeah, that's the overall strategy. It doesn't your answer? I'm sorry.
No, what I could say for the PIC64, we have an Ubuntu already prepared. Not that?
Mainline.
Mainline, okay. Sorry, I don't have this answer.
So yeah, also congratulations to Zephyr, to the T1S, the single wire Ethernet. Can I just hook together the PHYs without any like switch or hub in between, or how does it work? I don't know the bus. Yeah, can I just hook them together with cables and it's just a single bus, or how does it work?
Yes, the module itself, it requires right now today this sensor this module that we have, it requires SPI and I2C, but then in the near future we will have only 3 pins, and then everything will be included together inside the module. But from the network side, you need to have this T1S, this twisted cable network, and then you need to have a translator to exchange. You can have a USB connector, so you can connect directly the T1S to a computer or to a Raspberry or so on. So you bind the T1S network to the Ethernet network. This answers your question? Okay. Okay.
By the way, I just checked. The Microchip T1S driver is there in the Linux kernel under in the file section. So, yeah.
Oh, thank you.
So that's the only place we're going to look for code. So that's why we were kind of asking those questions regarding upstream and so on, because we just use the kernel or the Zephyr upstream and don't download SDKs and stuff, or we don't like to. Yeah. Thanks a lot.